So now we'll take a look at another variation of the limit notation that we can use to describe the behavior of a function. So these are the pieces of notation here. Let's start with reading them out loud and going over how they sound. So if you were to read this out loud, you'd say the limit as x approaches infinity of f of x. And in this one, you'd say the limit as x approaches negative infinity of f of x. And I want to make one thing clear at this point. Don't misunderstand this to mean that we're somehow now going to introduce infinity and negative infinity into our number system. They are not numbers, they're just concepts or ideas, right? If I write x approaches infinity, the idea I'm trying to describe is that x grows very, 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 very large, or x explodes in the positive direction, or x gets arbitrarily large in the positive direction. And in this one, if I say x approaches negative infinity, I'm just saying x moves very, very far to the left on the x-axis, or x explodes in the negative direction, or x grows arbitrarily large in the negative direction. Those are the three three phrases you could use to describe what this notation really is saying. Okay, so when we say the limit as x approaches infinity of f of x, what we're really saying is, well, what happens to the values of f of x as x explodes in the positive direction? Or if you use this notation, you'll say, what's happening to the values of f of x as x explodes in the negative direction? Okay, so really we're just using these pieces of notation to refer to the behavior of the output values from f as x moves very, very far away from the y-axis in each direction, right? This one describes the behavior to the right, and this one describes the behavior to the left. And you might hear some people refer to this as the end behavior of the function, so that's what we'll put here. So that is the end behavior of f. What happens to the output value of the function as x gets very, very far from the origin? Okay, so here's an example. Let's determine the end behavior of the function f defined by this rule. So f of x is equal to 1 plus 1 over x minus 1. And the first thing I want you to notice that this is actually the standard hyperbola shifted 1 unit to the right because of the subtraction of 1 from x. And then it's also shifted 1 unit up because of this extra plus 1 term. So let's just draw a quick sketch, and it will actually help us it's helpful to know in advance what you can expect to get for your end behavior, but also once we get the end behavior, it'll help us interpret the relevance of what we're actually finding when we actually determine the end behavior. Okay, so the standard hyperbola would just look like this. There would be a curve here, and there'd be a curve here. Right, but if it's shifted 1 unit to the right and 1 unit upward, then it's actually, you're going to have two asymptotes that intersect at the point 1, 1 in the Cartesian plane. And then you're actually going to have this sort of a picture. And then down here, it's going to come like that. And then like that. So it's actually, this is a standard graph that is well known to have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 1. Okay, well let's actually now discuss these limits and how you might actually evaluate them. So we're asked to determine the end behavior. So what that really means is find these two limits. So we're going to say, what is the limit as x approaches infinity of f of x? Well, we just started by writing down the notation. Let's actually replace f of x with what it means. So we want the limit as x approaches infinity of 1 plus 1 over x minus 1. Okay, and look at this as two separate terms. We've got one term which is equal to 1, and another term which is equal to 1 over x minus 1. Well, what's happening to the first term, 1, as x goes off to infinity? As x grows arbitrarily large. This 1 is just going to always be a 1. Nothing's going to change about this 1. But this fraction is going to change because what's happening? The numerator is always 1. And the denominator, what's happening as x grows arbitrarily large? Well, as x grows arbitrarily large, well then x minus 1 is also growing arbitrarily large. And if x is growing in the positive direction, then so is x minus 1. So what happens is you have a fraction whose numerator is always 1, but whose denominator is getting larger and larger and larger and larger. What's happening really is this fraction is really just going to eventually just become a really, really tiny positive value, and it'll become less and less significant the further x moves to the right. And really, where is this actually approaching? It's going to be approaching 0. It's because it's becoming insignificant. as x grows arbitrarily large. So then when we actually take this limit, that means this term is going to go off to 0. This 1 will still be there, and we end up with positive 1 as our limit. Okay, and really, how does that match up with the graph of the function f? So this is the graph of the equation y equals f of x. As x grows very, very far in the positive direction, or goes very, very far to the right, or explodes in the positive direction, what's happening to the y values? They're getting closer and closer to the whatever the line here is, this horizontal asymptote, which is at y equals 1. So the y values here are getting closer and closer to 1, which is really what we described analytically over here. So it comes down to making the observation that this fraction is really just approaching 0 as x gets large. Okay, so what happens as x goes to negative infinity? That's a pretty weak looking arrow. This is the limit as x approaches negative infinity of f of x. Well, that's going to be the limit as x approaches negative infinity of 1 plus 1 over x minus 1. Really, we can do the exact same analysis here. The 1 is going to be constant. This 1 won't be changing as x explodes in the negative direction. But as x explodes in the negative direction, something will be happening with this fraction. What's happening to this fraction? Well, the numerator is always going to be 1. And the denominator, well, if x is exploding in the negative direction, then so is x minus 1. Right? So really what these fractions are, what this fraction is going to be is a really, really tiny negative value. But it's still going to approach 0. Right? This is still approaching 0. It's just going to do it through negative values. So what you're going to end up with is 1. And again, this is corroborated by the graph. Right? As x moves very, very far to the left, what's happening? The y values of the points on the curve are getting closer and closer to 1. But they're always a little bit smaller than 1. Right? Because that's really just because this fraction is negative. Because as x grows very large in the negative direction, this fraction becomes small, but it's still negative. So that's why you're adding a very small negative number that just gets smaller and smaller and smaller. And that's so as you move to the left, the y values get closer and closer to 1. Okay, so there's a really nice correspondence between when these limits, you can refer to these as limits to infinity. That's really what these are called. If you take a limit to infinity of a function and you get a finite value in either direction, well, that's what tells you there's a horizontal asymptote at that value. So this we got 1 in both directions. So that means there's a horizontal asymptote that the function converges to in both directions. And of course, if you look at the graph, you can see that that's indeed exactly what happens. So this actually gives us a way to really precisely define a horizontal asymptote. So we can say that the line y equals L, so for example, think of the line y equals 1 in this picture. Y equals L is a horizontal asymptote of a function f if either, and there's two different ways this can happen, if either the limit as x goes to infinity of f of x is equal to L, that's one way it can happen, or the limit as x goes to negative infinity of f of x is equal to L. So if the limit as x explodes in either direction, to the left or to the right, of the function is equal to this constant L, in this case L is just some real number, then you have yourself a horizontal asymptote at the line y equals L. So again, just think of the line y equals 1, which is this flat line in this example. Okay, so you might also see a question worded like this: find all the horizontal asymptotes of a function. So we've got a function g of x, and it's defined to be this rational function, 3x squared minus 2x plus 1 over 5x squared plus x, and we want to find all the horizontal asymptotes. So really what that amounts to is we just want to find the limits to infinity. And when I say limits to infinity, I mean we want to find these two limits, right? That's how we're going to start these. And if you're ever asked to find horizontal asymptotes of any function, that's exactly how you're going to start. Just take the limit as x grows arbitrarily large in either the positive direction or the negative direction, and check both directions. Okay, so we'll start by taking the limit as x goes to infinity of f of x. What's going to happen? Well, let's start by unraveling what f of x actually means. Or, pardon me, g of x. Should be a g. I'll just scribble this out. and put that there. So that should have been a g of x, pardon me. So we got the limit as x goes to infinity of g of x, because that's our function here, g of x. Well, that's this fraction, right? So we have 3x squared minus 2x plus 1 over 5x squared plus x. That's our limit that we're taking. Now, it's not so obvious what's happening, because as x gets very, very large, well, our numerator is getting very, very large as well, right? We're going to take a very large number and plug it in for x. We'll have 3 times that number squared minus 2 times the same number plus 1. If x is very large, this numerator is going to be very large as well. And if x is large, then so is the denominator, going to be really, really large. Okay, but some of these terms matter more than others, and I'm going to show you why, and I'm going to show you how to determine what exactly this limit is going to be. And here's what we'll do. So just look at it this way. Factor out the highest power of x that appears anywhere in the numerator and the denominator. So in the numerator, we've got an x squared, so we're going to factor out an x squared. So we'll have x squared times 3 minus 2 over x plus 1 over x squared. And you might have thought for a moment, you can't factor out an x squared because there's only an x in the second term and there's no x's in the third term. And well, you still can, but you pay the price of introducing fractions. But it's going to turn out that that's not going to be such a big deal for us. So that's what we get. And you can check, if you multiply x squared back into the brackets, you can check that you'll get exactly the numerator here. And then the highest power that appears in the denominator is an x squared, so let's factor out an x squared there as well. And you might be able to guess what we're going to do here next, because now we've got a common factor of x squared in the numerator and the denominator, so we can cancel those out. And now our limit is going to become the following. Limit as x goes to infinity of 3 minus 2 over x plus 1 over x squared, and this is all over 5 plus 1 over x. Okay, so why is this any better? This may look awful because now we've got all these fractions inside of our larger fraction. In fact, so we've got 3 terms now that have become fractions. But remember how we did the previous example? We observed that as x gets very, very large, then 1 over x minus 1 just becomes arbitrarily small. It was easy to see that this fraction was going to disappear, right? And we've kind of set ourselves up for that situation now, because as x gets very, very large, well, x and x squared and x, which are the denominators of those 3 fractions, are going to get arbitrarily large as well. And the numerators of each of those fractions, 2, 1, and 1, are constant. So it doesn't matter how big the numerator is, if it's constant and the denominator is growing arbitrarily large, those fractions are going to eventually become insignificant as well. So that's how you can finish this off. This is going to go to 0. This fraction is going to go to 0. And this fraction is going to go to 0. So really what you're going to be left with is just the 3/5 at the end of the day. You're just going to be left with 3 over 5. So that means we found a horizontal asymptote of the function g. Y equals 3/5 is a horizontal asymptote. But we should check the other direction as well, right? Because we might have a different horizontal asymptote, because it could be 2. Sometimes you could have a function that has 2 horizontal asymptotes. So let's check the other direction. And it's good practice because we can work. The steps will be very similar, and it'll be good practice. So let's work through them. So we'll take the limit as x goes to negative infinity of g of x. So we're going to get the limit as x goes to negative infinity of 3x squared minus 2x plus 1 all over 5x squared plus x. Now, we could do every single step all over again, but let's try to recycle some of the work we already did. At what point did we actually ever take the limit and actually consider that x is approaching infinity? We didn't actually do that until we got to this step and moved from here to here. So starting from this limit to work to here, and to here, to get all the way to here was strictly an algebraic procedure. So all of those steps will be 100% valid still, because we didn't use the fact that x was going to positive infinity at all up until we got to this point, right? This was ignored all the way up until this step. So we can do the same thing. We won't worry about this limit. We're just going to do algebraic manipulations on this fraction, and we're really going to get the same thing we got here. So we're going to have the limit as x approaches negative infinity of 3 minus 2 over x plus 1 over x squared all over 5 plus 1 over x. Okay, so now let's see how, is this going to be the same as this, or might it be different? Well, we're taking a different limit, right? In this case, we're taking the limit as x goes to positive infinity. But here we have the limit as x goes to negative infinity. So x is growing arbitrarily in the negative direction. And again, I'm just going to remind you up to this example, how did these two fractions differ? When x is going to infinity or x is going to negative infinity, we have them both written down as going to 0. Remember why that's the case? If x is going to negative infinity, the denominator is still getting arbitrarily large, and that's what makes the fraction go to 0. It just so happens that if x is going to negative infinity, then the values of the denominator are going to be negative. So these will approach 0, but they're going to do it by running through a bunch of tiny negative values. So this fraction is becoming smaller and smaller and smaller, but all the while it's still going to be negative, but it's still going to 0. And that's the same thing that's going to happen here. 2 over x is still going to become arbitrarily small since the numerator is a constant, 2, right? And the denominator is getting arbitrarily large. It just happens to be in the negative direction. So this fraction really will be negative, but it's still going to go to 0. 1 over x squared, that's going to go to 0 as well. Actually, because the denominator is squared, the denominator is going to be positive. So this will actually be a fraction that goes to 0 through positive values. But since the denominator is growing arbitrarily large and the numerator is constant, that's really all it comes down to. That's all you need to conclude that a fraction is going to 0. If the numerator is constant and the denominator is growing arbitrarily large, whether it be positive or negative. Okay, so then our 1 over x down in the denominator, that will be going to 0 as well. So in this case, actually, taking the two infinite limits, one in the positive direction and one in the negative direction, was they were very, very similar. There really wasn't any difference in the work, but that's not always going to be the case, as we'll see in the next example. So you should make it a habit to always do both directions with completely separate calculations. Don't make any assumptions that they'll both work out nicely just to save yourself some work or do a shortcut, because what end up happening is you might miss one of the asymptotes, and that's no good. So in this case, we can answer the question. Let's say, therefore, y equals 3/5. Not and, there's just one horizontal asymptote, and it's an asymptote in both directions. So let's say y equals 3/5 is a horizontal asymptote of the function g. It turns out in our next example, we're actually going to have 2 horizontal asymptotes, so I must have been thinking of that one when I tried to write the word and. Okay, so we'll look at an example on the next page where it actually is going to matter which direction you're going.